Okay, so first of all, I created a Telegram channel, and it's very easy to find it using this link. And on weekends, I will send you a problem list, and I ask you try to solve some of the problems, because if you will not try to solve some problems, all these lectures will be absolutely unuseful. So there will be hints, and if you realize that you can't solve this problem, so you can just ask me. I will give you some more hints or explain some ideas, but I think that they're not very difficult. And I will send problems on weekends. Okay? So please subscribe to this channel. And also I would like to estimate how many students will try to pass this course. So who will try to do this? Okay. So last time we started to discuss linear systems on K3 surfaces. If we have a linear system, we define its fixed part. As one-dimensional base models, and its mobile part as mobile part of linear system L. And I'm sorry, I made a mistake last time. So let me repeat the lemma and the correct proof of this lemma, that on K3 surface S, the fixed part of any linear system is linear combination of projective lines with positive coefficient. And proof. We know that global sections of S are one-dimensional, so this is a rigid curve. So from Riemann-Roch theorem, and this is the place where I made a mistake, we obtain that its self-intersection is less or equal to -2. So it's not equal to -2, it's less or equal to -2. And from this, and from the fact that C is an integral curve in a divisor from this linear system, we obtain that its self-intersection is equal to -2, because for integral curve on a K3 surface, its self-intersection is always greater or equal to -2, and hence we deduce that C is isomorphic to P1, so its arithmetic genus is 0, and it's equal to its geometric genus. Okay. And now, yes, let me also recall that L is base point is called base point free if its base locus is empty and what is the condition on the line bundle? Who knows that it's base point free? How? Yes. This means that L is globally generated. And this means that we have a surjection from global sections to L. So this means that for any point S, there exists a global section that is non-zero on X. And this is, of course, equivalent to this condition, base point free. Okay, and now let me prove Kadeira vanishing theorem on a K3 surface, because in this case it's not very difficult. Kadeira vanishing on K3. What is the statement? That on an algebraic K3 surface, yes, we have the following vanishing and H1 S for an ample line bundle. For an ample line bundle L. And before we use this in a form that just follows from Serre duality, on a K3 surface. So we before we use this vanishing, but its immediate follows from this and Serre duality. So let me move this statement. So first of all, this part is immediate just because we can consider intersection of L with L dual, and it's strictly less than 0. So if we have a global section, then it corresponds to a curve, and L to an effective divisor, and L should be positive on an effective divisor because L is ample. So from this we obtain a contradiction. So this part is very easy. Yes? And now this vanishing is more subtle. Suppose first, suppose that there exists a divisor in this linear system such that it global sections on S is so the dimension of its global section is 1. So, for example, there exists an integral curve in this linear system. So, how we can now prove the vanishing? We can consider our favorite exact sequence S maps to OC. That tells you what? So the corresponding long exact sequence is the following: 0, maps to S, maps to maps to OS minus C and maps to H1. We know that S is a K3 surface, so we know that this vanishes. So this is one-dimensional. And we suppose that this is also one-dimensional. And from this, we obtain that this also vanishes, right? So if there exists such a divisor, then we obtain this vanishing, right? What we need to prove is the existence of such a divisor in this linear system. So first, we see that L is non-empty, just because from the Riemann-Roch theorem, its earlier characteristic that is less or equal to H2L from an ample line bundle, and this is 1/2. So we see that this dimension is greater or equal to 3. So this linear system is non-empty. Now let's take some divisor D in this linear system, and let us choose.
I'm sorry, I'm confused about the inequality over there. Shouldn't that be 2H0 because you need to add H2?
No. I mean that H2 is 0 for an ample line bundle, just because by sheer duality, this is equal to global sections of dual L. Okay, so now let's take some divisor in this linear system, and let's take a subdivisor in D with the following property: is the maximal subdivisor such that its global sections are C, so are one-dimensional. Of course, there exists such subdivisor always exists just because we can take integral curve. This is an effective divisor, so this is a linear combination of some integral curves, right? And we can always take one integral curve, then its global section will be one-dimensional. And now we suppose that, and now we take the maximal subdivisor with this property. So we cannot add to this subdivisor some integral curve in such a way that global sections will be still one-dimensional. Okay, and now a bit later we will prove that D1, D minus D1 is greater than 0. So this will follow from the Hodge index theorem, but it's a bit technical, so let me prove this statement in the end of the proof. And now let us suppose that we know this, that if we intersect D1 with D minus D1, then we obtain something positive. Okay, so what does it mean? This means that there exists an integral curve C in this divisor such that D1 intersects C positively. So from this we obtain what? We obtain that the global sections of C, OC minus D1, are equal to 0. Is this clear? Or I need to explain? Понятно? Okay. Is it clear? So we know this, and now let me consider the following exact sequence. OOC minus D1 is mapped to OC plus D1 is mapped to OD1. And how we obtain this exact sequence? So from two exact sequences. So here we have this. Here we have OS minus C minus D1. This is mapped to OC minus D1. And now we know that the cokernel of this map is just OC, because this is our favorite exact sequence. So we have these two exact sequence. This one, and this one. So three our favorite exact sequence. And from this we obtain that the kernel of this map is OC minus D1, right? So we have this exact sequence. Everything is clear, or I need to? So this is just a statement from homological algebra. So if we have two exact sequences and if we have map between them, then we have a long exact sequence of kernels that maps to co-kernels, right? This is a snake wave.
Yes.
This is a snake wave. This is called snake wave. So, so we obtain this exact sequence.
Можешь не стрелять? Можешь вернуть?
Вот, да.
Я не понимаю, вот тут написано H0 от S от линейного расслоения ассоциировано с D1, вот самое нижнее, вот глобальное сечение.
I mean that, no, yes, глобальные сечения, ну, у тебя достаточно много глобальных сечений, значит, ты можешь выбрать дивизор. Теперь ты хочешь дивизор, у которого глобальные сечения будут одномерные, ну, то есть как у... так. OD1. Sorry, I was wrong. I mean that OD1 is one-dimensional. So sorry. Yes, I mean this. So
it's like just taking the maximal connected component.
yes, and I take maximal connected component with this property. So sorry, this was a wrong notation. So Yes. So a basic example is an integral curve. So what I mean, so suppose that D is this linear combination, A1, C1, right? Then I can always take CI, right? And its global section of its structure sheaf will be one-dimensional. And I need this, okay? Because when I started to prove the Kadari vanishing theorem, it was enough to find a divisor with this property to prove the vanishing, just from our favorite exact sequence it follows. Okay? So yes, there we needed the vanishing of the one-dimensionality of structure sheaf of D1. Sorry. Thank you very much. So now we have this exact sequence, and now what we obtain from this exact sequence, we obtain that OC minus D1 maps to OC plus D1 maps to D1. And this is mapped to C minus D1. And what we know? We know that this vanish. Yes, we already proved that this is 0. And we know that this is one-dimensional. So from this, we see that this is one-dimensional, right? And this is a contradiction with maximality of D1, because we can just add C to it, and we...
minus why it's not 0? It's not 0.
That's because this is 0 and... No, it's not 0 just because this is an effective divisor, C plus D1. So it's always have global sections. This is a global section of the structure sheaf. It always is at least one-dimensional. We just don't need vanishing of this thing. This is always one-dimensional. Okay? So this is one-dimensional. And this is a contradiction with maximality.
It's because the curves intersect, it's one dimension.
What?
It's a global section of structure sheaf, you always have constants. But if it were two curves that didn't intersect, it could be two-dimensional.
Yes, but here we have, so this is 0, and we know that this is C. So we use that this is at least one-dimensional, and we use this exact sequence. Okay? And from this we obtain that this is one-dimensional, and so this is a contradiction with maximality. So the last statement that we need to prove is this one. So in fact, that we have positive self-intersection of D1 and D minus D1. And this follows from the Hodge index theorem.
Wait, what follows from this?
Let me remind that we suppose that D1 was in D was maximal subdivisor. I can use this. So we suppose that D1 is the maximal subdivisor such that its structure sheaf has one-dimensional global sections. And now we proved that we can add to D1 a curve C, right? And global sections will still one-dimensional. This is a contradiction with maximality. So from this maximal subdivisor, so from this we obtain what? We obtain that D1 is in fact equal to D that belongs to our linear system L. And this is enough to prove Kadari vanishing, as before, because if we find an element in linear system L such that its such that global section of its structure sheaf is one-dimensional, then we will prove Kadeira vanishing. It was the first part of the proof. I can use this. No. Yes. Suppose that there exists. Here was wrong. H4C is one-dimensional, right?
Yes.
Then we can use just this exact sequence. This is one-dimensional. We suppose this. This is one-dimensional. So this from the definition, this vanishing follows from definition of case-3 surface. So we obtain that this is 0.
Yes.
Okay?
Mm-hmm.
Как удобно с такой доской. And so it remains to prove this thing, right? That we have positive intersection of D1 and D minus D1. Any question? Everything is clear? Okay. So what we will prove? Suppose that we have an ample line bundle and we decompose it into effective divisor that where D is an ample line bundle ample line bundle and DI are effective non-zero divisor. Are effective non-zero divisors. Then I claim that their intersection is positive. So and this is our case. So D is just the sum of D minus D1 and D1, and this is two effective divisors. Just because D1 was a subdivisor in D. Okay, and how we can prove this? So we consider two numbers, AI, that are equal to D of intersection of D with DI, and then here we take self-intersection of D. Then what we have? We have that A1 plus A2 is equal to what?
1.
And we know that D is an ample line bundle, so we know that AI are strictly positive. So we know that these are some numbers between 0 and 1. Okay. And now let us consider divisor D. That is A1 D minus D1. So this is a divisor with cube coefficients, but we can consider divisor with cube coefficients if you want. And now what we have? Just from the definition of D tilde, we obtain that this intersection is equal to what? You just need to use the definition of D tilde. We know that this is 0. So from the Hodge index theorem, that is about signature of the intersection form. So we can consider Q coefficients when we are talking about signature. So from the Hodge index theorem, we obtain that self-intersection of D tilde with itself is what? Is so it's orthogonal to an ample line bundle, so it's less or equal to 0. And now how we can obtain the statement from this? Maybe
Wait, D tilde was ample. No.
D was ample.
D.
D was ample, and here we take intersection with D. So it's this divisor is orthogonal to an ample line bundle, so its self-intersection is less or equal to 0. And now what we have, we need to compute D1, D2, and this is equal to A1 D minus D tilde, A2 D plus D tilde, and this is equal to A1, A2, 0, and this is greater or equal to A1, A2, and this is greater than 0. Okay? So we just write D1 and D2 in a fancy way, yes, and then just compute everything and obtain this inequality. So morally, this follows from the Hodge index theorem, but we need to do some computations. Okay. Now we prove Kadir vanishing theorem on an algebraic K3 surface. Okay? Any questions? Comments? Okay. And now let us continue to discuss linear systems on K3 surface. So before this, let me recall what we have for curves, just because for K3 surface the picture will be quite similar. So suppose that we have smooth, irreducible, complete curve C of genus G. Then global section of its canonical bundle is what is the dimension of genus G?
2G minus 2.
No, it's degree, and the dimension of global section is G. Okay, and degree of the canonical bundle is 2G minus 2. And in fact, for genus greater or equal to 2, the linear system that is given by canonical class is base point free. Base point free. Or in fact, for elliptic curve, we also can say that it's base point free, because for an elliptic curve, the canonical bundle of elliptic curve is what?
Structure shift.
So it's also base point free. Okay, and now what we have? We have a regular map that is given by the canonical class to the projective space PG minus 1. And now we want to distinguish two cases. First case is when C is hyperelliptic, and the second case is when it's not hyperelliptic. So, for example, for G equal to 2, all curves are hyperelliptic. And hyperelliptic means that there exists a finite morphism from C to P1. No. There exists a double covering. There exists a ramified double covering of P1 from C to P1. Covering of degree 2. And for G equal to 2, this double covering is just given by the canonical bundle of C. And yes, for hyperelliptic curves, we always suppose that genus is greater or equal to 2. So P1 is not hyperelliptic curve. Okay. For genus 2, all curves are hyperelliptic, and the corresponding ramified covering is given by the canonical bundle. And for genus greater than 2, or greater or equal to 3, there exist both hyperelliptic and non-hyperelliptic curves. So there exists hyperelliptic and non-hyperelliptic curves. And in fact, the canonical bundle is very ample if and only if we have a non-hyperelliptic curve. So for hyperelliptic curves, we have what? We have a canonical bundle for hyperelliptic. We have a canonical bundle map to PG minus 1, and for hyperelliptic curves, this is the following composition. This is a ramified double covering of P1, and here we have just Veronese embedding of degree G. So maps to x0g, x0g minus 1, x1, and so on, x1g. Okay, so this is definitely so the canonical bundle isn't very ample just because this isn't embedding. This is a composition of unramified double covering of P1 and Veronese embedding to PG minus 1. Okay.
До степени G минус 1.
Okay. Да, right, because here we have an embedding of degree 2g minus 2 equal to the canonical bundle, here 2, and here is g minus 1. Thank you. So this is a hyperelliptic case, and not hyperelliptic. Curve C. So this is in fact this is non-hyperelliptic if and only if its canonical bundle is very ample. So for non-hyperelliptic curves we have an embedding for C to PG minus 1 of degree 2g minus 2. Okay? And now, this was just a quick reminder about curves. And now let me state what we have for K3 surface. So, preposition. Suppose that we have a complex K3 surface, and suppose we have a smooth curve. Is a smooth, reducible curve of genus G on S, then so first part we have already seen maybe 3 lectures ago, that the self-intersection of C is equal to what?
2G minus 2.
And the global sections OC is equal to what? We discussed this.
So we took the short sequence and then we did of C. Then we got two.
This G plus 1. Okay, so this is the first statement. We already, yes, as Alex said, we already proved this in such a way. It was easy. And now, the second statement is that if genus is greater or equal to 1, then linear system that is given by C is base point free. Sorry, I was is base point free, so it gives you map from a regular map from C to what? To what?
To projectization of the two global sections.
Yes, and what is the dimension?
The dimension is just G.
So we have a regular map from S to G, and the statement is that the restriction of this map to C is the map on C that is given by canonical bundle. So this is the map from C to what? To what projective space?
G minus 1.
G minus 1. So if we restrict this this regular map to C, we just obtain the canonical map on C. Okay, this is the second statement. Now the third statement is that if G is equal to 2, so if the corresponding curve is hyperelliptic, then this map is to what if G is equal to 2?
Q1.
No. Oh, sorry, S. S from C. This is P2. So this is a map of finite degree, and in fact this is a double covering, ramified in a sextic in P2. Okay? And now
No ограничение все равно. But the restriction on C is again just canonical map.
this is always true for
Yeah,
G equal.
Didn't see. Okay.
And we will obtain that this is in fact double covering from the restriction to C. We know that when we restrict to C, we obtain a double covering of P1 that is ramified in how many points?
In 6 points.
And we will obtain this statement from this. Okay, and now the last statement.
It's ramified what points?
It's ramified covering, double covering ramified in. So this is a double covering ramified in sextic curve in P2. And if we restrict it to the hyperelliptic curve, we obtain a double covering of P1 ramified in 6 points.
It's not the vice cross points. Will it be the vice cross points or not?
What?
The 6 vice cross points. Maybe it's still.
No. It's just in general sextic, so in a smooth sextic. No, so sometimes we can obtain. I don't say anything about. No, so sometimes we can obtain. I don't say anything about. About smoothness, but in any case, this will be just a sextic, okay? Maybe not smooth. And now the last statement is for genus greater or equal to 3. So in this case, we have both hyperelliptic and non-hyperelliptic curves, and so we obtain two subcases. So first is when phi is birational onto its image, in this case, a generic curve in the linear system C is non-hyperelliptic. And the second case is when phi is 2 to 1 morphism, and a generic curve in this linear system is hyperelliptic. Okay?
Is it two statements or two possibilities?
Yeah, for two possibilities. If a general curve is non-hyperelliptic, so we always have hyperelliptic or non-hyperelliptic curves. Okay, for G greater than equal to 3. There are just two cases. Okay, and if it's not hyperelliptic, then we have a rational morphism onto its image. So I mean that. So we have phi C. This is a surface inside PG. Surface. Maybe not smooth. Maybe it will have some ordinary double points. But in any case, this is a surface in PG. And what I'm saying is that if C is non-hyperelliptic, then this is a birational map. Okay? And if it's hyperelliptic, then this is a then it has degree 2. So it's a double covering. Okay? In a general point. So it can contract some divisor, but in any case, its degree is equal to when it's hyperelliptic, when C is a hyperelliptic curve. Okay, and now let me prove this statement. Is it clear? Okay. So I will prove this. So let me write down a proof on this board. Okay, so we can consider our favorite Z sequence. twisted by OC. And this is a global section that is given by C. Then, what is this?
The team.
Hmm?
Team is
No, dimension just.
So it's just 2G minus 2.
No, I'm not asking about global section. I'm asking about this line bundle on C.
Just
What is this?
canonical bundle.
Yes, this is from the adjunction formula.
Right.
From adjunction formula. We obtain that this is a canonical bundle. Okay, and now what we have for the long exact sequences of global sections, this is OC. And this is and here we have. So we know that on a K3 surface this vanishes. So we have a surjection here, right, from the global sections of C to global sections of canonical bundle of C. So we see that dually this is a hyperplane inside a hyperplane given just so here we have a global section that is induced by C.
we need to take dual again.
Yes, dual. By this global section, right? So, and from this, we immediately obtain that the restriction of C to C is just the canonical embedding, right? And now why it's base point free? Just because base locus of C is definitely contained inside C, right? And we know that the canonical line bundle on a curve of genus greater or equal to 1 is base point free. So from this we obtain that C is base point free. Is base point free. Okay, so we proved this statement. And now, before we will prove 3, 4, let me state what we have now.
Can you say again why it's base point 3?
Just because base point of the linear system C is definitely contained inside C, right? And on C, the restriction on C of this linear system is base point free, because this is just the canonical bundle embedding. Or no embedding, the canonical bundle map.
Yes.
Okay, now what we have proved so far, that for G greater or equal to 2, we have a regular map to PG, and phi C of S is a surface in PG. And in fact, we also proved that 2G minus 2 is equal to self-intersection of C is equal to degree phi C times degree of the surface is this clear, or I need to explain this thing? It's better to explain?
Second line is adjunction? Or
No. Oh, what I mean that
это
if we have...
предложение или утверждение?
Вот это утверждение.
Сверху, выше.
А, вот это утверждение, ну это понятно. Я про это. Для g больше, if g is greater or equal to 2, then we obtain that this is a surface inside PG. Just because in this case C is mapped to so a general member of a corresponding linear system is mapped to a curve here. So it will be a surface. I'm asking about this thing. So for an elliptic curve, we just here we have a map to point, yes, but for genus greater or equal to 2, this is a map to
Все в одну. Случайно.
an exercise. Okay. So do I need to explain this thing?
Yeah, please.
Okay. So suppose we have a map between two surfaces. This is surfaces, and suppose that degree. This is a generically finite map, and the degree of P is equal to n. Then what I claim that if we have two divisors, D1, D2, and C, two effective divisors. No, for simplicity, two integral curves. Then their intersection, D1, D2, will be equal to n times their inverse images. Okay, and is this clear? Is this statement clear? So first, what's this one?
Just in case, if D2, for example, is the ramified locus, does this still hold true?
Okay, for simplicity, let us suppose also that D1 and D2, and this is in fact our case, because what we have that C is a restriction of a hyperplane here to S. Yes, so if we have if we restrict two hyperplanes, if D1 and D2 is the restrictions from hyperplanes on S prime, then this is true. And I think we can, in general, we can always.
Там n с другой стороны должен быть.
Oh, right. Sorry. And here. So I can explain geometrically what we have. So we have two integral curves, D1 and D2, and suppose that they intersect properly. And in the case when we have
But it is better to write that C is pullback, yes, because it's not always embedding. No, it is a bit.
But here I wrote a pullback. No.
That C is restriction H on S. It's
Yes. Well, here we have a. Here it is a pullback of H.
Yeah. Uh-huh.
Yes, and this is equal to degree of VC, and this is what we have here. This is
yes.
okay. And why this is true? It's clear. Just because if we have two divisors that intersects properly, right? Two curves that intersects properly, and here is a generically finite morphism, then their pullbacks will also intersect properly, and the number of the intersection of P D1 with P will be exactly n, the degree of the corresponding map, to D1 to D2. Okay?
But if they don't intersect problem,
Hmm?
what if they don't intersect problem?
Then I think that it's not true. So if we can find two divisors in if we can find two divisors then intersects properly in the corresponding linear system, this will obviously hold, and I'm not sure that this will be true for rigid divisors. That so for I don't know -2 curve and
But
so
we
on.
always may.
If we can deformate them in such a way that
But we don't need
okay.
to deformate in an ineffective way. So we may.
Okay, yes. So if we have a moving lemma and for an intersection we have a moving lemma, so we can always deformate them in a such a way. So maybe yes, maybe it's always true. So what I mean that if when we deformate in a linear system divisors, we use effective divisors. So we need to find two effective divisors that intersect properly. But in general, we can deformate divisor in such a way that it will be not effective. It will be still linearly equivalent to D. So what I mean is that it's when you can always, I don't know how to say this in English, сдвинуть дивизор с точек. We can always move the divisor from some points, right? So we can always find a divisor that is linearly equivalent. So the statement. So if we have D, some divisor, we can always find divisor D prime that is linearly equivalent to D. And for any points P1, P2, Pn in the support of D, we can find a linearly equivalent divisor D prime in such a way that P1 and Pn will be not in the support of D prime. Okay? So, of course, if we consider just effective divisors, this is not true because we have base locus, for example, right? But for some divisors, some maybe non-effective divisors, we can always find a linear equivalent that is that doesn't contain P1 and Pn in the support.
Yes.
Okay?
Yeah, and even we may как-то obtain the situation where all intersections are transversal.
Yes.
Bertini theory.
Huh?
Bertini theory.
No, not Bertini, just
So you want
you.
to see on crossings.
Yeah.
Is it clear or not? So, and now, do you understand this formula? Everyone understands this? That we have, that the intersection of C and C, that is the pullback of H, of the hyperplane section here, it's equal to degree of the map times degree of the corresponding surface. Okay?
But how are we sure that C is rigid in the image?
What?
How are we sure that C is rigid in the image?
Where?
Just use
Here?
this argument.
Here? Or what?
This is a parity rigid.
Or I don't understand what to ask. Where? Here?
Okay. I think it's fine.
Okay. So we have this formula, and now what do we have next? Now we can prove all the remaining statements. So for genus equal to 2, we obtain a map from C to P2. And this is a subjective map. The degree of phi CS is definitely 1, right? Just because this is P2. And so from the above formula, we obtain that degree PC is equal to 2. So this is a generically finite morphism of degree 2. And now let us consider its branch locus, and suppose that it has degree n, degree of the branch locus, and we know that if we restrict this map to C, then we will obtain the double covering of P1 ramified in 6 points, right? In n equal to 6. So n is equal to intersection of the ramification curve with the corresponding P1, and this is equal to 6. Right? Just from Hurwitz formula. So we obtain the statement that this is a ramified covering of P2 in a sextic curve. Okay?
Why is that?
Just because suppose that, so we have a branch locus, it has some degree, right? Then if we restrict it, now we know that if we restrict the corresponding map to C, we will obtain a double covering of P1 ramified just exactly in what points? In the points of intersection of...
Yeah, but what if this P1 is conic? Why why this P1 cannot be conic in the image? It is obvious?
Yes, just because...
yes, C is just pullback of hyperplane.
Why is it 6?
Why it's 6? Do you remember Hurwitz formula? That if we have two curves, then what we know, and degree and map P, and map P, then 2 GC minus 2 is equal to what? And degree of P is equal to n. Is equal to what?
N multiplied by G of C prime minus 2G of C prime minus 2 plus something about ramification.
So in this case, we have what? We have curve of genus 2, and here is curve of genus 0, right? So how many points are in the ramification for this formula? So in this case, we have degree is equal to 2.
Yes.
Here it is equal to 2. This is equal to 2 minus 2 minus 4 plus error. So the number of so there are exactly 6 points in the ramification, right? And this 6 points is exactly the number of points in the intersection of the curve with P1, and this is exactly the degree. This is by definition the degree of this curve. So this is a sextic. Okay?
Okay.
Yes. And now what? We still have some time. And now what? And now we need to prove the last statement. So for hyperelliptic and non-hyperelliptic curve. So suppose first that C is non-hyperelliptic. So we have an embedding of C to PG, and we know that its restriction is the embedding of C into PG minus 1. So we see that C times C is just the degree of the corresponding surface. So just because, as before, C is the restriction of the hyperplane here, right? So from this and from the above formula, we obtain that degree of C is equal to 1. So this is the aberrational morphism to its image. Okay, and what does it mean that this is aberrational morphism? This means that there exist an open subsets U and C here, and U prime and phi C, such that phi C induce an isomorphism between them. Okay? And now suppose that we have a curve, a smooth integral curve in the linear system C. Then we see that its image intersects this open subset U in a non-empty way. So we see, from this, we see that the restriction of C to C prime is aberrational morphism to just because its image intersects U in a non-empty way,
To see
right?
non-emptiness,
So it's an open subset in image, and this is a curve. So we obtain a aberrational map from C tilde to its image.
why cannot C tilde just be complement to be a closed locus?
No. There exists. So this is a aberrational map. So we already know that.
Скажу, почему C с волной лежит в дополнение до с волной, наверное, C с волной общий.
No, it's a general, of course.
Generic.
Okay.
Generic curve. So, and as the statement was about generic curve in this linear system. So I want to prove that generic curve in this linear system is non-hyperelliptic. And so for generic curve, we obtain that this is non-empty, and this map is birational.
And
Okay.
in the assumption, you assume that C is also generic, yes?
Yes, of course.
It
No,
may be so that C is hyperelliptic, but generic.
yes, suppose that suppose that. Okay, maybe I need to denote it like C prime, but. Okay, suppose that there exists a generic curve is non-hyperelliptic. Then we obtain that the map is birational, and we need to obtain that all generic curves are also. No, I don't need that. So it's just enough. Why it's not enough to assume that C is non-hyperelliptic? I think it's
Я
not.
не знаю, просто может такое быть, что сама C гиперэллиптична, но при этом все, остальные...
No, I'm trying to prove that no. That for a generic curve, here we have a birational morphism. So this is birational. And we know that this restriction is equal to omega, just using the same argument as in the second statement. We know that this restriction is the canonical bundle on C tilde. So we know that C tilde maps by its canonical bundle birationally to its image. And we know that the canonical bundle, so for curves so we obtain from this that a curve is non-hyperelliptic, okay? Just because the canonical linear system on curve is very ample if and only if the corresponding curve is non-hyperelliptic.
Yeah.
Okay? So I think it's enough. To assume this. Okay?
But then it is excluded for all curves in this linear system they are not hyperelliptic, not for generic, no. Is it possible that in this linear system there are only one hyperelliptic curve? I think that it's impossible because we have a bidirectional map and
If I look at this two-dimensional matter than 2, then it could be true, but it must, for rational movement, it must conject some minus curves.
I think
I think it's possible to have a contraction here. So sometimes we will have a singular surface in the map. So there are some -2 curves are possible. But I'm not sure. I need to think. I'm pretty sure that the image can be singular.
Yeah, I believe it can be singular.
And there is some contraction in this case.
And this contracted curve may be hyperelliptic. Or
I think they can be anything, but I need to think. Okay.
I mean,
every contracted curve is orthogonal to C, if I remember correctly.
okay, yeah.
So it should be.
So no, there are no curves in linear system that contract. I think that there is no possibility to have hyperelliptic curve in this linear system at all.
Okay, maybe yes, but I need to think more accurately. Okay. Okay, and now.
Okay.
Okay, and for C hyperelliptic. We have what? As we discussed, C by its canonical system is mapped to P1, that is a double covering, and then it's mapped to PG-1 by Veronese embedding, and in fact using just so we know that from above formula we immediately obtain that this is equal to 2. From this we immediately obtain that self-intersection is equal to 2 degree of phi c s, and so degree of c is equal to 2, and using the same arguments we can prove that the generic curve in the corresponding linear system is hyperelliptic, should be hyperelliptic, and the degree is 2, so this is a 2-to-1 morphism. Okay? And what next? Okay, let me, we have still, okay, we still have 2 minutes, so let me state the last proposition, and I think that to prove it, it will be an exercise, but I will send you this exercise on weekend, and I will give you all hints. So it will be, with these hints, it will be not very difficult. You will just need to use all these formulas that we discussed before. So what is the proposition? Proposition. So for any G, there exists a K3 surface G minus 2 that is embedded in PG and that has a degree okay. How to prove this statement? So you will need to consider three cases separately. So when G is equal to 3K, G is equal to 3K plus 1, and G is equal to 3K plus 2. And in fact, what I want to explain in 1 minute is the following statement that is very general, but you need the statement to prove this. So what I want to recall you is that so if we have some smooth variety and we have what does it mean to be smooth? Not even surface, just smooth variety. What does it mean for a divisor to be very ample? Is very ample on ifs. This is if and only if it separates points and separates what?
Tangent vectors.
Mm-hmm.
Yeah.
Separates.
Smooth projective properties.
Smooth projective. Mm-hmm. Projective variety separates tangent directions. Is it clear? Everyone knows this statement? Yes? Or I need to. So okay, it's separates points means that for any PQ and X there exists a divisor D in this linear system such that support of D contains P and support of D don't contain Q, and separate tangent directions means that for any point and for any vector in the tangent space, the risky tangent space, XP holds XP dual, there exists a divisor D in this linear system such that P is in the support of D and such that V doesn't lie in the P dual. So this is the Zariski tangent space 2D, and this is a subspace here, right? And we ask a divisor, a tangent space of the divisor do not contain V. Okay? And in fact, it's possible to show that it's not so difficult to show that the linear system is very ample if these two holds true. So, and from this, what can we deduce from this? That if our X is inside Pn, so we can restrict hyperplane section to X, and suppose that there is a linear system that is base 0.3. Then from this criteria, we can immediately obtain that the linear system is very ample. Okay? And using this, we can prove, I will send you an exercise when you will prove this by your own. So to prove the existence, we need just to construct a very ample divisor D and X such that its self-intersection is equal to what? From the above what we discussed. So we need to construct a very ample divisor with 2G minus 2. And using this, you will, all in each of these cases, you will construct a very ample divisor in such a form that has this self-intersection. I will send you it on weekends. Okay? So thank you very much. Я опять могу выключить. Помогите мне.